Hi, I'm going to show you how I implemented a backpropagation-free method to train a neural net and actually got it to the same accuracy on the MNIST dataset as backpropagation. So this is based on this paper that came out a few months ago, Evolution Strategies at the Hyperscale. And basically it's obviously about evolution strategies, but the authors introduced this way of not using full rank noise perturbations, full rank matrices for the noise, but low rank versions, even rank 1 perturbations, which is what I'm only using in my implementation. But they still achieve full rank updates when the population is sufficiently big. And they also introduced some neat computational tricks to never actually materialize this full-shaped version, so the outer product of the vectors, but to only work with these vectors in the whole algorithm. So yeah, let me in the meantime start the comparison of EGGROLL, so of this algorithm which I implemented, and then of the same thing but just with backpropagation, just to have a look at the results and the performance. So here's also a nice pseudocode of the algorithm, but what I want to show is this. So basically what the authors suggest, which makes this much more efficient on top of using low rank perturbations, is that usually you would have for a forward pass, a standard forward pass in a neural net, you would have this matrix multiply, and in ES you have this mu is your mean weights or your main weights, or the weights you do perturbations from, and then this is the actual perturbation. So sigma is the hyperparameter that controls the spread of the noise, and E is the actual noise matrix. So this we deconstruct into our low rank matrices, or rank 1 vectors that we're using. But this obviously is very expensive, because this is happening over the whole population, which is the number of perturbations we do, or number of workers. And the authors see that this can be split, because here now we have only a single matrix multiply on the left, and on the right, now that we have low rank perturbations, we have these vectors B and A, and we don't have to materialize the outer product, because we can just do a vector-vector product here with X directly. We get a scalar here, and then have a scalar vector product, and that's exactly what I did in my implementation. So you can see here I'm using JAX, and JAX's own pseudo-random number generator. I'm saving the keys here because we're not saving the perturbations throughout, because we need them for the update. We are reconstructing them in the update on the spot. So I have these functions where I pass in the keys for the noise and for the noise generation, and the X, and then I'm creating the noise vectors, and you can see here I'm doing the vector-vector product, and then scaling A by this, and that's basically pretty simple. And then this is what I'm then actually scaling the weights with over the population, doing the forward pass from the second layer on. I'm also using a separate input for other workers, and then for the fitness scores, which is what we are using to weight the perturbations by, to move into the direction of highest fitness score. I first used just a standard thing we would in backpropagation, which is cross entropy, but realized it's actually much more stable, and it converges much better when I use just the raw training accuracy. And so that's what I did here. And then I'm ranking this and normalizing it just to keep the variance constant. And then for the update, I'm also using a trick the authors did, because for rank 1, it's nice to actually put the perturbation vectors in two matrices with the population over the population, and then here for the update we can just do we can weight the vectors in A by their respective fitness scores, and then do a big matrix multiply, which is then just over the whole population. And that's also what I did here in the update. So I'm reconstructing A and B matched over the population, and then here I'm doing this weighting by the fitness scores, and then the matrix multiply and scaling, because we have to take care of our normalization here in ES. Yes, that's basically the main idea. And now that the comparison also finished, we can look at this. So just to say, I used so a learning rate schedule for ES, and also sigma schedule, so the noise spread. But I also did a hyperparameter search for backprops, so for both, just to have a fair comparison of what both are capable of. And the architecture of the models that the two algorithms are training is the exact same batch size, same number of epochs, same number of hidden units. And we can see in the results that EGGROLL, or evolution strategies, here gets to 97.84% accuracy on the test data, and Backprop gets to pretty much the same result. But we have to look at wall clock time here, which is still 2 orders of magnitude slower in evolution strategies on EGGROLL. And also the memory the memory demands are still much higher in EGGROLL. But this is more of a proof of concept for me, just to see that this actually works. I can get to the same results with no backpropagation. This actually allows for non-differentiable components and new optimization objectives potentially. Here I'm using raw training accuracy as my signal, which Backprop would never allow. And this is here not making a difference yet, but there might be creative ways to change things in models that Backprop doesn't allow, but ES does, and which can lead us to interesting ways of doing things. So all this code is on GitHub. You can look at it there. If you find anything that is not right or could be done better, I'm open for feedback. Or if you've done an implementation and want to share it, please get in contact and let's have a chat.